So sorry. I hope you can hear me now. We're just trying to put some things in place. Good morning, everybody. With our time fast spent, I think I should just give you the first attendance code, which is 7R77G. It is 7R 7R77G. I hope you have it already. All right. Elijah, I can see you. If there is any comment, yeah, good morning, Mary. God bless you. Now, I'm going to rush this because I know that you are all preparing for one test or the other. Am I right? I was told mathematics test is supposed to be for today, and physics is for tomorrow. Chemistry is on Wednesday. So let's quickly go through group five. The same way we've been going through the others is the same way we're going to go through group five. Okay? Now, let's quickly look at it. Group 5 elements, obviously, they are otherwise known as the group 15 elements in the modern IUPAC table. And the major thing about it is that they have 5 electrons as their valence electrons. And they have a general formula of NS2 and NP3. You will see that of all the elements that we've been dealing with, this is the most stable. This is the most stable. And they are characterized by the presence of lone pairs of electrons. That makes them very, very important. I'll be very, very fast today to see how far we can go because I'm planning to let's see how far we can go. My plan to give you a physical class later this week. I don't know because of your test, but it can still be arranged. Whatever arrangements you have, you can come and meet me. Okay, look at the first table, group 5 elements. We have nitrogen, we have phosphorus, we have arsenic, antimony, and bismuth. And you will see that all of them have 5 electrons in their outermost shell. You can see from the end, you can see that they have different energy levels. The first element belongs to the second energy level. The second one belongs to the third energy level. And that is the reason why most of the time nitrogen cannot expand its octet as well. The only thing it can do is to form a positive ion, like when it forms an ammonium ion. This ammonium ion is formed by the aid of the lone pairs of electrons that it has. Obviously, it is going to have an anomalous behavior. And part of the anomalous behavior is the fact that it can operate in several oxidation states from -3 to +5. You can see it there. While others are just centered around 3 and 5, 3 and 5, 3 and 5. And just like I told you, as you go down the group, the tendency to form compounds in the low oxidation state abounds. You can see that if you look at it, you will see that in this case we have more than one what? We have more than 4 electrons in the outermost shell, and the oxidation states will be that number of electrons in the outermost shell and 8 minus the number of electrons in the outermost shell. We're talking about 5 electrons here. We're now talking about 5 itself as an oxidation state, and then 8 minus 5 as the second oxidation state. Variable, we also have various coordination numbers, and those in brackets are the most stable ones. Like it has occurred in virtually all the group 3, 4, and 5s. You always see that there's always a member of that group that has a very, very short that has a very, very short lifespan. We call it half-life. And this in this case, for group 5 elements, it is Moscovium. The occurrence, you can see here that it is said that the 6 elements in the group uh, make up less than 0.2% of the Earth's crust. But nitrogen is very, very important. Nitrogen is the most abundant element, is the most abundant gas. And this is the reason why the use of nitrogen is controlled. This is the reason why nitrogen cannot be used in the free state. It must be used in a combined state. Otherwise, if it is used in the free state, it will definitely kill all the plants that we have. And if plants are killed, there will be no life. I want you to go through all these highlighted um, things that I've given you in your notes. Nitrogen exists as a diatomic gas so that it can be neutral. Phosphorus is the 10th most abundant element in the earth crust, and it is important in ecological metabolism and so on. Another thing I want you to take note of about the elements in this group is that two of their members are essential elements in the production of fertilizers. Essential elements in the production of fertilizers. We have nitrogen, we have phosphorus. The next one is potassium. And we know the reason why potassium is there. I don't know whether you were taught that potassium has a higher mobility. It transports signals, it transports nutrients faster than any other element in this case. How they are found, they have been given here. I want you to draw me back if I am going too fast. But I think that since you had this note, since you have this note, you should have. I'm trying to look at your comments. Yes. Tell Adebayo Emmanuel that the class has started already. Now, we are talking about these elements existing in the earth crust. Always remember that they are going to occur as what? As ores. Fluorapatite and hydroxyapatite are the two ores from which phosphorus can be obtained. Phosphorus is also very, very important because it is a major component of our insecticide. It is a major component of our insecticide. A lot of us wouldn't be alive today if not for the effect of the organophosphate insecticide, which helps in protecting us and also trying to protect the plants by getting rid of the pests. Let's quickly look at the allotropes. The allotropes of group 5A, 5A elements or group 15 are given here. Two allotropes are known for nitrogen, and they are the what? The alpha and beta nitrogen. White phosphorus has several allotropes, but the red and white phosphorus are the most critical ones. So you still have black phosphorus. You are still going to see it here. And then there can be interconversion from one form of phosphorus to the other. Phosphorus exists as a P for tetrahedral molecule in the gaseous state, and it can also exist in the solid phase. And the one that exists in the solid phase is the white phosphorus. And then you can interconvert the tetrahedral molecule to a linear molecule. Now, in this case, for the first two members, they also exhibit p-pi bond. P-pi bond, just like carbon, but it is nitrogen that exhibits it most. It is nitrogen that is why nitrogen can form several kinds of compounds in various oxidation states. Of all the elements that you studied, 3, 4, and 5 groups, you will see that it is only nitrogen that has the ability to react with both oxygen, hydrogen, and other compounds, and then form various compounds in different oxidation states. I want you to take note of this. It is said here that rapid cooling of phosphorus, the tetrahedral phosphorus in the gaseous state, gives a brown phosphorus, which contains the what? Diatomic molecule of phosphorus. If the white phosphorus is now heated above 260 centigrade for some time, the less reactive red phosphorus is what? Is formed. Red or violent form that is less reactive, and black that is what? The most stable and the least reactive. I want you to take note of this. We can point out questions. We can point out questions anyhow from this. Look at the interconversion of phosphorus. This is the beauty of phosphorus. We don't have this in nitrogen. That is because nitrogen ideally is in the gaseous state. So the handling of nitrogen becomes very difficult. How this was done has actually been explained. Arsenic exists as gray, the gray is the metallic and the crystalline type of arsenic, and the yellow is the what? More reactive form, while antimony exists as yellow, and so on and so forth. I don't want us to waste too much time here, but anything that I have marked here or have labeled, you have to actually take note of them. General properties: nitrogen and phosphorus are considered to be non-metals. Arsenic and antimony are metals, while bismuth is what? Metal. This is not too far-fetched because as you go down the group, metallic character increases. As you go down the group, size increases. As size increases, electropositivity increases. As electropositivity increases, the reactivity also increases. And when you are studying, I want you to do it this way. You look at all the parameters taught in group 3, compare it with what you have in group 4, compare what you have in group 5, because there could be comparison in your questions. There could be comparison in your questions. But always remember, as you are moving from one group to the other, from the left hand side to the right hand side of the periodic table, from the left hand side to right side of the periodic table, you see that the sizes are what? Decreasing. And this is what is responsible for the differences in their reaction. The valences plus 3 and plus 5 are shown with the tendency to, okay, let me quickly read this. There's a tendency for the pair of electrons. Okay, this is important. There is a tendency for the pair of the electrons on the s orbital to remain inert. So only the p orbitals, the p electrons are used in bonding and trivalent compounds results. What is this trying to tell us? You know, I told you that there are two stable oxidation states. We have the plus 3, we have the plus 5. Obviously, the plus 3 state is equally stable because when you lose the three electrons in the p orbital, ideally, the 3 electrons in the p orbital is also stable. But when you lose those 3 electrons, the next orbital is fully filled. That is the s orbital that adds 2 electrons. So you can, for instance, you can form compounds of phosphorus as with halogen as PCl3 and PCl5, and the two of them will be very, very stable. But like I told you, I told you in my first class, I told you that the lower the energy level, the higher the stability. The lower the energy level, the higher the stability, which is an indication that the plus five compounds are going to be relatively more stable than the plus 3 compounds. Let us look at the various oxidation states that is being exhibited by nitrogen. You will see here, and the compounds as well. You will see here that this is not with only oxygen, and that's the uniqueness of nitrogen. It is exhibiting excessive compound formation at various oxidation states. When you compare it with carbon, this is because of the presence of what? Lone pairs of electrons. Take note of all this, and then you can also calculate their oxidation state as you are looking at them. Now, look at the next line that was highlighted. There is an increase in both the atomic and ionic radar down the group, but the progressive increase is likely affected by the presence of what? Fully filled d and f orbitals whose electrons are what? Poor shielders. We've been emphasizing this since we started teaching part 3. Okay. Ishaya wisdom, that means that tendency to form plus 3 oxidation states increases down the group. That is very, very good. Very, very good. You are now applying what we've been talking about. When I see comments like this, I get encouraged. I get to realize that I'm not actually wasting my time, because I wouldn't want to set questions that most of you wouldn't be able to answer. But with this, it's quite, and I think I know some of your names offhand based on your responses, but the attendance has not been too good. And this is going to affect you, whether you like it or not, because my own section is not a section that you can just cram. Let's look at the ionization energy. If size does what? If size increases down the group, ionization energy is expected to do what? To decrease down the group. The smaller the size, the higher the ionization energy, because the higher the effective nuclear charge. But like I told you, as we have experienced in group 3, in groups 3 and 4, we are still going to experience it in group 5, because after the second element, the size does not increase as expected. There is a slight increase, but it is not significant enough to affect the ionization potential. It is definitely going to be different, but you must always note that the size increase is not as much as expected. Okay, so the ionization energy might be slightly higher because the size is not as big as it is expected to show. Now, take note of this. The energy required to produce the M5 plus ion. This is one of the reasons why the plus 5 compounds might not be easily synthesized. The plus five compounds might not be easily synthesized. This is because the energy required to get to the plus five state, that is the ionization potential required to get to the plus five state, because this is going to be go from one state to the other. First ionization energy will be added to the second, will be added to the third, will be added to the fourth. This energy are directly or indirectly related to the activation complex. And compounds will always look for an alternative where minimal energy will give them a strong compound. That is why most of the time you don't get the plus five states compound. That's why you don't get the plus five states compound. I want you to take note of that. Mhm. Now, fluorine is the only element that gives a large enough electronegativity difference to permit ionic bond formation. I explained this in the last class. Fluorine has the highest electronegativity. So if an ionic compound is going to be formed, because the size is increasing down the group, but it is not increasing as expected, it means that it is also not going to be as electropositive as it is expected to be. And you know that ionic bonds are formed when the difference in the electronegativity value between the elements that are forming the compound is large. But if you don't have a large size, you cannot have a large electropositivity and a low electronegativity. This is the reason why it is only the species that has the highest electronegativity that would give a large electronegativity, that will exhibit a large electronegativity difference between the element, group five elements, and itself. Fluorine is so that is the reason why fluorine, when you form compounds of fluorine, especially with the large elements towards the end of the group, you will see that ionic compounds are formed. Therefore, compounds like SbF3 and BIF3 exist as what? Ionic solids. Okay? M3 plus ions are rapidly hydrolyzed in water to give this. Let's look at electronegativity as well. Okay. I have Ayuade Peter. I have a seating arrangement. I will check it down so that you don't get confused. Um, when when I told you last Friday that your chemistry test might be coming up this week, and we were sent some papers. I'm trying to see. This is going to slow me down a bit, but it is important for us to academic. Except if it has been changed. Your test was slated for 17th. Your test was slated for 17th. And it's going to be an all-day thing. But if there are changes, when I get to the department, I'm going to talk to the coordinator so that we can pass on the right information to you. Electronegativity. Electronegativity decreases down the group. Electronegativity does what? Decreases down the group. Why? Because size increases. Okay? Electron affinity also decreases down the group. Electron affinity decreases because with large sized elements, they have a higher tendency to lose their electrons. That is why metals easily lose their electrons. When the size is large, the effect of the nuclear charge is not as pronounced, so they easily lose their electrons. An element that is ready to lose its electron will not have an affinity for electrons. That is why electron affinity will decrease. And you must note this. It has been explained. It has been explained. And show it not to Lulokwe until it is confirmed, which I can even do now. Your test, it has been slated for 17th, okay, which is Wednesday. Hold on. Wow. Okay. Please, let's quickly. Hey, Bro K. Ẹ káàárọ̀ sir. The 17th date is still holding for the test. Aha. Children, ẹ ṣé gan sir. Children, but some of them are misinforming themselves. They are saying that the chemistry test is not for this week. That's why I'm calling now. Thank you. I'll pass on the information. Sir, what did you say, sir? Okay. Wednesday 17th. Okay. Wednesday 17th is the date for your mid-semester test. Okay. Don't be deceived by anybody. Show it to Lulope and Ayuade Peter. Take note of it. Your test is coming up next tomorrow, and it is starting by 8:30, I guess. Yes. By 8:30. Please take note of this. Inform every other person. Inform every other, because if you miss the test, there's no catch up for it. Thank you very much. Okay, Eshigo. Yes, sir. All right. Rejoice. I don't know. If you organize that, I will make myself available for that. Presence of lone pairs of electrons. This is what characterizes group 5 elements. They all have lone pairs of electrons, but the way they lose these electrons is different. This differentiates the properties of groups 3 and group 4 from the group 5 elements. The presence of lone pairs of electrons does a lot. That is why they are used as catalysts. That is why they are used as catalysts, because they don't need any other thing to initiate a reaction. The presence of lone pairs of electron actually helps them in initiating reaction. The second attendance code for today, the second attendance code for today is K for T double three. K for T double three. K for T double three. All right. Well, Adeoye Grace, if it is organized, the revision class that will cover everything that I've been teaching you will take place in one case theater. That is the largest lecture theater we have, except they want us to have it at amphitheater, which could have been very, very ideal. Now, let's look at the variation. The rate at which they lose their lone pairs of electron also vary, because they all form tetrahedral compounds. They form tetrahedral compounds. And in these tetrahedral compounds, three of them are the real bonds, and the fourth bond, the fourth site, which is supposed to be a bond, is now occupied by lone pairs of electrons. Look at the last line here on page 4. The ease of electron release decreases down the group. The rate at which they easily give out their electron decreases like down the group. That means that nitrogen nitrogen, the smallest member of the group, is going to be the one that would readily release his electron, as compared to what? As compared to bismuth, which is the largest. In fact, most of the time, we don't talk about the chemistry of bismuth because of its low stability. Can somebody give me the reason why nitrogen is going to readily lose or give out its lone pair of electrons? Can somebody tell me that? Well, anyway, I'm waiting. Good. Okay. I'll be waiting before the end of the class, though our time is fast spent. Look at the way, because of the presence of these lone pairs of electron, they usually form dative bonds with electron deficient species. With electron deficient species, they form dative bonds. That is, they are electron rich. They are ready to give out, to share their electron. If you look at the equation that we have here, we have Na3 with boron trifluoride. You all know that boron trifluoride is boron trifluoride a nucleophile or an electrophile? What is the definition of a nucleophile? Anyway, it is boron trifluoride is going to be electron deficient. And if it is electron deficient, What is responsible for this is that the three fluorine atoms surrounding it are pulling electrons from it. That is, they are exhibiting minus inductive effect, pulling electrons from it. So the fluorine would the boron is going to be electron deficient. It is going to carry a delta negative charge. And because it is carrying a delta negative charge, it will want to satisfy this deficiency with electrons. And nitrogen, a nitrogen compound or nitrogen itself, will now donate these electrons. Not totally. It will donate it for the two of them to share it. And the rate that and the kind of bond that is going to be formed between them is going to be called a dative bond. A dative bond is a covalent bond that is a covalent bond that is formed when only one species out of the two combining species to form a compound donates the electrons to be shared. The reason why it is covalent is because electrons are what? Shared. Why are group 5 elements good reducing agents? They are good reducing agents because they readily donate their what? Electrons. And reducing agents are usually what? Oxidized. Okay, let me read G1, group 1 and 3 elements. Hold on. I noticed that for group 1 to 3 elements, the boiling and melting point decreases down the group due to the weakness of yes, metal. But why is that of group 4 and 5 increasing? That was why I told you that there is a peculiarity in group 4 and 5. And this peculiarity has to do with the presence of the lone pairs of electrons. Not to worry, all these things will be explained to you when I have that. I don't have much time because we have something like a 15-page paper here, which I'm not too sure we'll be able to finish today. And I really want you to go through it. But you can reach out to me directly in the department. Okay. But it is not too difficult. It is not too difficult. Let us reason it out together. Why do you think the melting point, the boiling point would increase? Why? I need an answer from you, suggestion, then I'll be able to give you the right answer. Let's look at nitrogen. Okay. We also said that their basic nature is due to the presence of lone pairs of electrons. Anyway, we all know that already. Nitrogen cannot expand its octet, so its coordination number can never be greater than 4 period 2 elements. Okay, because it belongs to period 2. It is not possible for it to it is not possible for it to expand its octet. I've explained this one very, very well. But every other member of the group, yes, you are getting closer. Liz O5, you are getting closer to the answer, but not to worry. Let me quickly go on. You will see that phosphorus can form PCl5, can form PCl6. That is because it is a period 3 element, and it can expand its octet into the d orbital. And every other member of the group should be able to do that as well, apart from nitrogen. You can see here that nitrogen differs for every member of the group because of the p-pi multiple bond that it exhibits with some elements. Now, take note of it. Take note of this. The bond is not easily broken. That's why it has a high not okay. You're getting closer. Nitrogen has a special peculiarity, unlike carbon. You know that carbon forms its p-pi bond with only oxygen, but nitrogen can do so with several elements. That is why you will see it forming it with itself. You will see it forming it with hydrogen. You will see it forming it with oxygen, and these different ways. It goes a long way to form it with carbon in the cyano compound. This is the peculiarity of what? Nitrogen. And that is because despite the fact that it can exhibit the p-pi bond, it was enhanced by the presence of lone pairs of electrons that was absent in carbon. Metallic character increases down the group. You all know that. And there's always a decrease in electronegativity because the size is what? Increasing. Well, as usual, the first two members of the group are not real metals. They are not obviously nitrogen is a gas. We're now saying that nitrogen and phosphorus are what? Are non-metals. You will see that when we're talking about the type of the allotropes of phosphorus, we told you that some of them are existing in the gaseous state. Some of them are existing in the gaseous state. Dynastic, or what's this thing? Maybe you are dynamic or whatever, asking about my topic. Well, I should be able to tell you this tomorrow, though I'm set, but they are yet to ask my questions. You know that they are just going to roll the questions out. They are yet to ask my questions. Okay, but I would prefer my questions not coming out in your test so that I can have this physical class with you and better explain so that you can have better understanding and then you can apply it to the other parts that you must have been taught. Antimony, which is the third member of the group, is a metalloid. And the metalloid shows what? Both metallic and non-metallic character, while the other members of the group, which are what? Antimony, no, bismuth, arsenic. You see, phosphorus and arsenic are considered to be metalloid. Now, antimony is supposed to be a metal, but it behaves partly like a non-metal. But bismuth is obviously behaving like a metal. It is actually a metal. Go through the table 3.3. AOC. Well, I don't know. Every member, everybody that has taught you, particularly the first three or four people that taught you, will ask questions, but I cannot predict where the questions will be coming from. Yeah, taking my time by sending these questions. Now, look at the first ionization energy, second ionization energy, third ionization energy. You will see that as we go on, as the ionization energy increases for each element, as electrons are being lost, you will see that the ionization energy is doing what? Is increasing. Is increasing. For instance, when you lose the first electron in the P3, you will see that the first ionization energy will be low, will be relatively what? It will be relatively low. Look at use the rules I gave you concerning ionization energy. More than half field, less than half field, more than half field, less than half field. Take those ones into consideration. Look at the electronegativity too. Electronegativity is decreasing. Look at those things that I have already explained in the other. Let's now quickly look at the compounds. Hydrides. These are compounds with hydrogen. Group 5 elements will form volatile hydrides in the form of what? MH3. Why? Because it is believed that elements in the plus 3 states are much more easily formed. Why? Because the energy required to form compounds in the plus 5 oxidation state is what? Is very high. The ability to use the lone pairs of electrons to coordinate on this is the ease of replacement of hydrogen by the other groups. You see, they form, when they lose these electrons, they lose these lone pairs of electrons, it is easier for them to form compounds with hydrogen. The preparation of ammonia in the laboratory is given next. Let's look at arsenic. When you are talking of arsenic, you are talking about the halide of arsenic. You are talking about the halide of arsenic. Let me quickly give you the third attendance code. And then the third attendance code today is HGVS8. HGVS8. That is the third attendance code and the last attendance code. Let's quickly go on and see if we'll be able to go on. Now, the arsine is the halide of arsenic, while stibine is the halide of antimony. They are formed by the reduction of a trivalent arsine and antimony compound. They must be the reduction of what? By the reduction of trivalent arsine and antimony compound. What are we saying in essence? Addition of hydrogen is what? Reduction. But so whatever compound of arsenic and of antimony, when you reduce it, for instance, with hydrogen or any species carrying hydrogen, you are going to form their hydride. You are going to form their hydride. The stability of the hydride decreases down the group. Why would the stability of the hydride decrease down the group? This has to do with what? The electronegativity and the what? And the bond length. As the size increases, the bond length also increases. As size increases, the bond length also does what? Increases. And as the bond length increases, the stability decreases. A very long bond will be much easier to break than a short bond. Stability. Okay, okay, okay. Let's go to their halide. Like I told you, like I told you, everything that I've given you in your notes is very important. But I have highlighted some things that will help me explain the principle to you. That is why some things are highlighted. They are not supposed to be highlighted. If this class had not been an online class, of course, there wouldn't be anything like this. I would just have been giving you, and you would have had a better understanding. But the situation we found ourselves, you have to cope with it because you don't have a choice than to pass. Halides, these are compounds with what? Halogens. Elements of this group form binary halides with two stable oxidation states. That is, they have the ability to form halides in the two stable oxidation states, plus 3 and what? Plus 5. Why were they not able to form halides in the plus 5 states? Apart from the fact that the energy required to form compounds in the plus 5 state is very high. Can anybody answer? You are just concentrating on this attendance code. Concentrate on what you are teaching you, whether you like it or not. A lot of these questions will come. If they don't come in your test, they'll come in your exams. Concentrate on this. If you look at hydrogen, it has low electronegativity. That is one. And it is not ready. It does not readily release its electron. Okay. But when you are talking about a reaction with halides, halides are highly electronegative in nature. And this species will now act like pseudometals. And there's going to be a good interaction between them. They form trihalides and pentahalides. Okay, the trihalides are represented as MX3, and then every member of that group will form compounds where X is actually halogen. They are usually volatile, easily hydrolyzed in water. Now, compounds like NF3 is stable, but NCl3 is what? Explosive. When the compound is explosive, it depicts instability. It depicts what? Instability. Look at nitrogen. It's a very small entity. Go back to that table. Look at its electronegativity. Compare it with the electronegativity of chlorine. You see that their sizes are very close. And because of the closeness in this size, nitrogen would not be able to accommodate chlorine. But nitrogen would easily accommodate fluorine because fluorine is very, very small. And it does not form an ionic compound with it because of the small size of nitrogen. But with any other member of that group, it will easily form an ionic bond, which is going to make it extremely stable. So NF3, that is because of the size. The small size of fluorine allowed it to form a compound with nitrogen. But the larger size of chlorine made it a little bit impossible. They were forced upon each other, and it means that they are not unstable. That was why they are said to be what? Explosive. NBr3 and Ni are known only in their unstable harmonies. The same thing explains it. Nitrogen, and even if it cannot form a stable compound with chlorine, why would it form a stable compound with a larger atom, a larger species like bromine and iodine? They all resemble covalent halides because they are extremely unstable and explosive. PF3 is very reactive. PF3 is very active, and it is used as a precursor in the manufacture of what? Some organic compounds. Okay, let's look at their pentahalides. Maybe I have just a few minutes. Um, Maybe we'll be stopping around this pentahalides, and then we can look at the oxides tomorrow. We can look at the oxides tomorrow. Let's quickly look at the pentahalides. The time is almost up. They have to work on this. But let me just introduce you to the pentahalide. We told you they can form compounds uh, with halides in the +3 and in the +5 state. Now, the pentahalides, all the elements in the group would form pentahalide, except for what? Nitrogen. Except for what? Nitrogen. When you are forming compounds in a higher in using a higher coordination number, the smallest member of the group that cannot expand its octet will not definitely partake in it. Pentahalides like PF5, PCl3, BR5, ASF6, SBF5, and SBCl3 are all known. And this is because of what? This is because um, of the differences in their sizes. And you will see that I can ask you that which of them is going to look ionic out of all these compounds that we have here. Obviously, we can have PCl5, not PCl3, not PBr3, but ASF6, and so on and so forth. I will stop here and continue from here tomorrow. I wish you all the best in whatever test you have today and the subsequent ones. Do have a nice day. God bless you all. Thank you.
No, they could just slide it. Okay, move fair. Okay. I'm not the type I want to write on it. Okay. Okay. Am I online now? Good morning. Good morning, class. If you are there, can I just see your response? Yes, 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 yes. Ezekiel is here again. Good morning, good morning. We want to start PHY 102 now. PHY 102. How was your weekend? And I believe you are fully ready for the test tomorrow. I can only pray for you that all shall be well. And I wish you good success tomorrow. Thank you very much. So if you can still remember, last week, Wednesday, we started with a magnetic field due to current. On last week, was it last week Monday? We started with magnetic field due to current. And I tried to introduce the course to you by actually explaining to you that assuming we have a wire of an arbitrary length, so an arbitrary shape, and we want to actually determine the magnetic field at point P. So from there, I said the permeability multiplied by the current dot ds sine theta all over 4 pi r square. And not only that, we move ahead. I assume that, let's assume that we have a very long infinite wire, that the wire is very, very long. We don't even know the end. And we are to determine the magnetic field at a certain point, very close to that long wire. And we assume that we already determine the magnetic field to that magnetic field at that particular point P to be mu I all over 2 pi r. And I said also that assuming that the wire is not long wire, but is a semi-infinite straight wire. And I said it's going to be mu I all over 4 pi r r. And also, I said, assuming that we want to actually determine the magnetic field due to a current in a long straight wire, the one with that we have that is actually in a we have the diameter of the wire and we have the radius of the wire. And if you want to determine the magnetic field outside that straight wire, we said we are going to actually get this one. And if it is inside, we are going to apply this one. And if you can still remember vividly, I said for us to determine the direction of that particular current, we use what we know as a right-hand rule. And not only that, we said if we want to actually determine the magnetic field due to a current in a circular arc of wire, we actually determine that one that we are going to take the central angle, which is in radian, into consideration. Okay, so and also we move a bit further. We actually solve this simple calculation on Monday as well, and I actually show you. I did it for you, and I show you what I actually have here also. And not only that, we actually did. I asked you to actually take a picture of this classwork, and I remember that I dictated the solution, the answer to you, and I actually give you the hint on how to actually solve the question 1, 2 to 3. And today we are going to start with the two current carrying wire exert magnetic force on one another. But before we move further, let me quickly give you the attendance code for today. The first attendance code is 4TA9Q. That is 4, T for Tango, A for Apple, 9, and Q for coin. I hope you have the attendance code now. 4TA9Q. Okay, thank you very much. So this morning we are going to start with two current carrying wire exert magnetic field on one another. But the first thing we need to understand here is this: when we have two wires that's actually carrying current. If the direction of the current is the same, they have the same direction, like this one, if they have the same direction like the one we have here, one thing that will come to our mind is that the two of them, they are going to attract each other. And if the direction of the current are opposite, they are going to attract each other. Please take note of this particular part very well. I said if we have two long parallel wire carry current, exert forces on each other, and to find the force on a current carrying wire due to a second current carrying wire, the first thing we are going to do is to determine the field due to the second wire at the side of the first wire. Assuming we want to determine the magnetic field of this one, we are going to actually determine the magnetic field of that one due to the second one. Okay, then after we have done that one, we now find the force on the first wire due to that particular field. But one thing I want to understand here to solve this, the problem related to this one is this. Let's assume that we have this guy, this is the first wire, and we have this wire, this is the second wire. So if you look at this one, and as you can see, the direction of the current is this, right? That is moving down like this one, this is the direction of the current. So for this one, it's actually moving like this one, okay? Like this one is going up like this one. Okay, so assuming we want to determine the magnetic field at the middle point here, what we have to do here is that it's going to be the total magnetic field is equal to the magnetic field with that of the first one, which is one that is going up, and the second one is going down. That means it's going to be minus B2. Okay. But I will still explain this one to you when we get to it. I'm going to use a simple problem to actually explain that one better. I just want to understand that when we have a two current carrying wire, if the direction of the current is the same, they have the same direction, they are going to attract each other. But if they are anti-parallel, they are going to repel each other. So as I've said from the first slide, and you still remember that for the magnetic field of this wire A, okay, and this wire B. So the magnetic field of A acting on at B is going to be this one. Okay, and when we get this one, to determine the force is going to be the force FB that is produced on a wire B due to magnetic field of B is going to be this one, okay? And that is the field due to A at the position of B, we create a force or B. So, and since we know that L, the L here is a vector length. So we are going to say the vector L and B are perpendicular. If they are perpendicular, that shows that the angle there is going to be sine 90 degrees. Yes or no? Okay. So from there we can now say the force B relative to A is going to be the current of A multiplied by that L multiplied by the magnetic field of A sine 90 degrees. And for that, this sine 90 is 1. Our BA is this one. We can quickly substitute for this particular one there. So there we can now say the direction of force FBA is the direction of the cross product L cross product of BA. Are you following? Okay, just to explain better this simple for you to understand this one very well, let's quickly use this simple example to understand it. Okay, if you look at the first question, though it's homework, but I will give you an hint that will actually help you to solve it very well. And when we come on Wednesday after, I'm going to actually ask you although I've already shown you the answer, I will seek your opinion. If there's all of you got it right, it's fine. If there's still some, if you are unable to get it right, maybe if I don't have the time, I will actually solve it in the slide that I will send to you at the end of this part. Okay, but first of all, to explain this one to you, first thing you need to understand here is this. Look at the question 1. We said 2 long straight wire. Let's say we have the wire like this, and the other 2 long straight wire. Okay, this is the first one, carrying current in the same direction. That is, if we have this and this, let's assume that the current is actually going up like this one. Okay, so we can see that this is I1 and this is I2. Okay, so from there you can see that the magnetic field is actually going. What they said was to calculate the magnetic field at the midway. This is the actual midway. Okay, so from there we can say the magnetic field is going like this. So that shows that it's actually going up like this. Okay, this is B1. Okay, and that of the second one is actually coming from this side, going like this. Okay, going down like this, which is B2. So the total magnetic field here is going to be B total equal to B1 addition of all the magnetic field. So B1 into, let's say, plus into minus B2. As you can see, the B2 is actually going downward. Okay, so but since we are to determine the magnetic field at the midpoint, at the midway, so that's why the distance, which is distance between the two of them, is 0.4. So but since it's midway, the D is going to be 0.2. That is midway, 0.2 centimeter. But mind you, you are still going to convert it to centimeter. So if you can still remember the formula there, for since our B is the 2 or is this particular one, so we are going to have what we know as this one. It's going to be this, since we have our B equal to mu naught all over 2 pi D into I1 minus I2. Okay, so from there, if we substitute this one into the actual formula, we can actually determine our magnetic field at the midway. So since we know the mu to be 4 pi times 10 to the power 7, and we know our D to be 0.2 times 10 to the power minus 2, okay, because converts 0.2 centimeter to meter. And same time, as we know, we have the current I1 equal to 8, I2 equal to 12. So that is going to be 8 minus 12, which is going to be 4. So from there, if you substitute that one into this one, you should be able to get this particular answer. But mind you, you may actually probably you got the negative as the magnetic field, but don't bother yourself about that one. That's so that it depends on which one are we actually consider first. Are we consider the B1 first or the B2 first? That is what actually brought about the negative sign for the magnetic field. But mind you, the answers will be this one. Okay. So now for the second one, the difference is that the second one is opposite direction. That is, it's going to be B equal to B1 plus B2, not negative. That's so that it's going to be current I1 plus current I2. That is the difference between the two. Okay, just make sure you can see that I both this one, same direction and opposite direction. Try to understand it very well, because for you to know who actually understand it or not, I am going to actually use this one to confuse you. That is, if you use the same direction, you will find your answer there to be correct answer. And you will still find the answer for the opposite direction there, just to know if you are actually understood what I explained or not? So for the the third one is very, very simple. You are to determine the correct the force. That is, you remember the formula there. Thus, the two currents will appear there, multiply them, and you will get the correct answer. Okay, let's continue. So, how many of you are following? I know my students will say no, 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 that you are not following. How many of you are following? Yes or no? Please, small. Okay, 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 okay. But did you get what I'm trying to say? What I'm trying to say is that when we have current carrying wire, if they are of the same direct, oh, no, 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 no. I know you will say no, no, no. So 0.42, because it's the midway, you divide the 0.4 by 2 and you will get 0.2. Okay, and at the same time, I said, since the magnetic field of the current, if the magnetic field is all that is the same direction, that's so that the B magnetic field direction up and the other one down. So it's going to be B1 plus into minus B2. Okay, it will only affect the current. Okay, so for the second one, since it's opposite direction, that's so that the magnetic field, they are going to face the same direction, up, up, up. So you will add them together. And for the other one, as I've explained to you earlier. So now, to actually explain Ampere's law to you, we want to apply the Ampere's law to loop that encircle current. So if you want, what you can see here, that we want to actually determine the net electric field due to any distribution of charge, as has been determined. If you can see, remember my colleague that taught you electric field, he actually explained something on a Gauss law for you. Is more or less the same thing with Ampere's law. Okay, so the loop on the integral sign means that the scalar is to be integrated around a closed loop, which is what we know as Amperian loop. So the current I enclosed is actually the net current encircled by the closed loop, that is this one enclosed by the closed loop. Okay, so if you use to actually use the Ampere's law, if you just curl your right hand around the Ampere loop with the finger pointing in the direction of integration, you can see that a current through the loop in the general direction of your outstretched tongue is assigned a plus sign, and a current generally is in the opposite direction is assigned negative. Okay, so if you can still remember, if we use the argument similar to that of Gauss law, we can say that of Ampere's law is equal to this guy, which is integral of B dot ds equal to the permeability multiplied by the current. Here, there are three things that you need to understand here. And either this is the benefit of attending classes. Here, the first thing is that the Ampere's law is not dependent on the shape of the curve around the current. So the curve is not dependent on this one. It's also not dependent on the current passes through the curve, but it only depends on the total amount of current through the area enclosed by the integration. Take note of these three. Take note, take note, take note. The reason is that in multiple choice question, I can give you maybe Roman figure 1, Roman figure 2, Roman figure 3, and say which of these one are actually correct, and I will mix the one that is correct with the one that is not actually correct. As you can see, when you see that, oh, the Ampere's law is depend on the shape of the curve, you know that one is not correct. So, you know, if you say current passes through the curve, not correct, but it only depends on the total amount of current through the area enclosed by the integration part. Do you understand? Okay, thank you. Take note of this one, and when you get the slide also, make sure you actually master this particular aspect very well. Okay, let's assume that we want to determine magnetic field. inside a current carrying wire. The first thing you need to know is that we have the diameter of the whole wire to be R, and we have the diameter of the inner to be small r. Okay, so in this particular area, in this particular one thing that you need to actually come to your mind here is this. So you remember that we were determined in the secondary school field that current density is equal to the current all over the area. Okay, so we can now say the current through the wire is equal to the current density times the area of the circle. So you still remember the area of the circle equal to pi r square. So let's assume that we have a uniform current density with I, which is the current enclosed, which is the total current passing through the wire. If you now come here, we have this one. If you do the substitution, compare the one inside and the one outside together, we are going to arrive at the magnetic field inside a current carry wire to be this particular one, where we have B equal to permeability multiplied by the current multiplied by the radius, the radius of the inner, all over the 2 pi r square. So you need to recall that outside, the magnetic field outside is equal to the B equal to permeability multiplied by the current all over the 2 pi r. Am I communicating? But let's now imagine in case a semi-circular ball in a sharp edge is still independent of the intuition. Yes, yes, Alpha, you got it right. Okay, so what we are saying here is this. So if we want to determine the magnetic field inside a current carrying wire, this is what we are going to apply to it. Okay, so that is take note of this, please. Are you following? Take note of this. That is magnetic field inside a current carrying wire. The inside the wire, the magnitude B of the magnetic field, we know that is actually proportional, that is, B is proportional to the R, right? So, but mind you, at the point, at the center here, the magnetic field there is 0. Why? Because the R there at the center, not at this point, is 0. So from there we can say the magnetic field at the center, we have this one, we have this. So D is the center. The magnetic field at this place is proportional to the R, but at this point is actually equal to 0. Mind you, so also R is the maximum when small r is equal to bigger R. Am I communicating? That is, I said inside at the center, the magnetic field is 0. At this point, the magnetic field is directly proportional to the R. That is, the greater the small r, the greater the magnetic field. But if the small r is equal to bigger R, that is, if this one is equal to this one, we are going to have the maximum magnetic field. So that is, the two equations give the same value for B at the surface. Thank you. Okay, let's quickly use this simple homework to see if we actually understand what I've taught you. Look at this question. A long straight wire carrying a current 3.3 ampere, okay, enter a room through a window 1.5 meter high and 1.0 meter wide. The path integral is, which is this guy, around the window frame as the value. We were to determine this particular integral B dot ds. But mind you, still remember is equal to mu I. But they say find the integral of this one around the window, that's outside the window. So all this one, you don't need it. You don't need all. What you need is just 4 pi times 10 to the power 7 times the current, 3 ampere. So anything you get is going to be 3.8 times 10 to the power minus 6. Am I communicating? The reason is that we are to find the integral of B dot ds around the window, meaning outside the window. Meaning outside around the window, meaning outside the window, not inside the window. Okay, so if inside the window, the answer may be different, but outside the window. Thank you. Okay, let's now apply the magnetic field. We want to determine the magnetic field of a solenoid. I know all of you know the solenoid. Then when we have a wire that we actually, it's just like how many of you have seen the coil for pumping machine before? Or so that coil is that they want it around a particular object. So that's in form of a solenoid. Okay. So here, one thing to understand here is this. We want to apply Ampere's rule to solenoid. That is, it concerns the magnetic field produced by a current in a long, tightly wound helical coil of wire. Such coil is called a solenoid. That is, it produces a uniform magnetic field. Now, let's assume that the length of the solenoid is much greater than the diameter. So as you can see, we have figure A is a solenoid carry current I. Figure B is just a section. After they just cut it to make it easy for us. So the solenoid magnetic field is the vector sum of the field produced by the individual turns that made up the solenoid. So for point very close, take note of this one, the one I underline. For point very close to a turn, the wire behaves magnetically almost like a straight wire. But outside the solenoid, the magnetic field there is zero. Take note. Please help us to slow a bit. Okay, thank you very much, Ayodele Taiwo. What I'm trying to say here is that, okay, let me quickly give you the second attendance code before I continue now. H L K 99. H L K 99. H K H L K HLK99. Thank you. Please help us to. Thank you very much, Da Mayor. So what I'm saying here is that when we have a magnetic field of a solenoid, it actually behaves like a long straight wire, although it's actually one round. It's a particular object. So I said something here. I said if we want to determine that any magnetic field outside the solenoid is equal to zero. Okay, so I said for point very close to a turn, the wire behaves magnetically almost like a long straight wire, and the line of B, they are almost concentric cycle. So if you look at B, figure B suggests that the field tend to cancel between adjacent turn. It also suggests that at point inside the solenoid and reasonably far from the wire B is approximately parallel to the solenoid axis. Okay, so for this particular one, the best way to understand this one is this. Let's use the next slide to actually explain it better. Okay, as you can see, this is a solenoid, just dissect in a way that will make life easy for ourselves. And we have let's assume that we have let us now apply Ampere's law to this particular one, since we said the Ampere's law is equal to the mu times the current enclosed. So for us, you can now say to determine if we have a uniform solenoid that is outside any magnetic field outside here, the magnetic field is equal to zero. Okay, so look at this particular equation. We want to, that is, the Ampere's law is equal to the sum of all, that is, we can write as sum of all the four integral, that is integral from A to B, B to C, C to D, and D to A. So as you can see, if we integrate A to B, which is B dot ds plus B C dot B dot ds, another integral C to D, B dot ds, D to A, B dot ds. Here, one thing to understand here is that I said magnetic field outside outside the solenoid is equal to 0. So which one is outside here? CD. That is, CD is equal to 0 because magnetic field outside is 0. And if you look at the second one, and this one is going to be 0 also because the magnetic field can either perpendicular to DS or is 0. Since this one is not, the two of them are not perpendicular to the DS, definitely they are going to be equal to 0. So from there we can now say this one is going to give us this and the first one. And if we integrate A to B, which is equal to the H, we are going to have this one equal to BH. Okay, so from there we can now say that thus integral B dot ds is equal to, for the entire rectangular, is equal to B times A. So inside the solenoid carry current I at point not near its end, the magnitude is equal to this particular one for an ideal solenoid. But mind you, that small n is the number of turns per unit length. That is, n is equal to number of turns per unit length. That is the number of turns present and the length of that turn. Okay, that solenoid. Okay, so if we now move a bit further, we can apply the same thing to toroid. So as you can see, toroid is just like a circle. So that is which may be described as a hollow solenoid that has been coiled until its two ends meet, so forming a sort of hollow bracelet. So what magnetic field B is set up inside the toroid is more or less the same thing with that of solenoid. The only difference is that we know when we are trying to derive that of solenoid, we say the integral from A to B there is H. Okay, but in this case, H is equal, this one is going to be 2 pi R because of it's a circular form. Okay, so from there we can now say this guy is equal to B dot 2 pi R equal to the mu naught I all over n. So, and mind you, that n is the number of turns here. So from there we can say to determine the magnetic field of a toroid is going to be mu naught I n all over 2 pi R. But mind you, in contrast to the situation for solenoid, B is not constant over the cross-section of a toroid. Am I communicating? So under the toroid, something that you need to understand here is this. In case I'm not actually giving you calculation to solve, I just give you some just to know if you actually understand it. The principle here is this: for magnetic field of a toroid is inversely proportional to the radius of that particular toroid. So that is, if the radius is very wide, definitely the magnetic field will be smaller. And if the radius is smaller, what is going to happen to the magnetic field is going to actually be larger. Okay, am I communicating? So that's so that the field of a toroid decreases with increasing radial distance. I repeat myself. The field of the field or the magnetic field in a toroid decreases with increasing radial distance. That is, B is directly proportional to 1 all over R. Okay, so we can say a toroid has a square cross section with the length of a edge equal to the radius of inner surface. We can now say the ratio of the magnitude of the magnetic field at the inner surface to the magnitude of the field outside. Okay, is what we know as this particular one. Am I communicating? Try to take note of the difference between that of solenoid and that of toroid. Mind you, that of solenoid, I said the magnetic field outside the solenoid is equal to 0. And I say the magnetic field at this particular one and this one is equal to 0 because the magnetic field can either perpendicular to the ds or is 0. And since this one is not perpendicular, these two are not perpendicular to the ds, that's why we say is equal to 0. I'm trying to actually recap what I've said earlier, and I said the magnetic field is equal to the, for the solenoid, is equal to the mu multiplied by the current multiplied by the number of turns per unit length for an ideal solenoid. Okay, so and I said for toroid, the magnetic field is inversely proportional to the radius, to the radius, that is to the radial distance. Okay, so if we now move a bit forward, just to solve this particular problem, to see if my students are actually following or not. How many of you are following Ezekiel? I can see, oh, yes, you are following. I hope I'm not too fast today. I know my friends will say I'm too fast, but trying to actually understand what I'm trying to pass across to you. Look at this simple example. You are given a solenoid. The length of that solenoid, we call it N, equal to 0.5 meter, okay? And it has 3 layers of a windings of tongue, and that our N, capital N, is equal to 750 ton. But they said 3 layers of it, that is, to get the actual ton, multiply that one by 3 for the actual ton. So you are now to determine, and we are giving the current to be I equal to 4A, okay? And you are to determine the magnetic field at the center of the solenoid. Remember the formula, equal to mu naught this I n. And since we say it's going to give us mu naught I dot multiplied by the n all over L. That is, you can now say 4 pi times 10 to the power 7 times 4 times 0.5 times 3 times 750 all over that of the length, which is 0.5. So if we do it correctly, this how can you see it now? We are giving 3 layers. But mind you, as I used to tell you, if you forget this particular 3 layers, you will find your answer there, though it won't be the correct answer. That is, we have 3 layers of windings of a ton, of 750 ton. Right? We have 750 inch. That is the first one 750, second one 750, third one 750. Making times 3 of this one, we give us the number of ton. And you remember the number of ton per unit length, which is this particular guy, and it's going to give us N all over L. So from there, we can actually get the right answer. Can you fast a little, sir? Oh, Oluwadamilare, that is one thing with life. You cannot satisfy everybody. Don't let us be too fast today, okay? Thank you very much, okay? Why is the numerator being multiplied? I did not multiply. Numerator is 0.5. 0.5, which is the length, okay? Not multiply, okay? Is divide. So we multiply 3. 3 is the number of turns, and 3 is the layers, and number of turns is 750. 4 pi, 4 is the current. The 0.5 is the length. That is, since L, small n, is equal to number of turns per unit length. Is that okay? All right. So now is what I just saw for you is what you have here, in case you did not follow the way I did it for you there. Okay. So if we go to the next classwork, sir, cannot see the complete question. The 750 is not showing. Yeah, it's supposed to be showing. It's not showing from where I saw it, right? But mind you, it's 750, but I mentioned it now. If you cannot get it here, it's still the same thing here. Can you see it here? Okay. It's showing now. Is the long in the question. 0.5 is long. It's length of the solenoid. Okay. So the next question is this. You are giving this particular one. They said a solenoid of 1.3 meter long and 2.6 centimeter in diameter, carrying a current of 18.0 ampere. The magnetic field inside the solenoid we are given to be 23.0 millitesla. We are to determine the length of the wire forming the solenoid. This question is very simple, and if you don't pay attention to understand the question very well and you just rush into it, I'm sorry, you may not get the answer. So, but please and please, you are to determine the length of the wire that actually form the solenoid. So to start with, first of all, let's determine the number of turns that are actually present first. If we determine the number of turns, that is, if we determine the n first, that will actually help us to determine the n all over l. Is that okay? Okay. So now, the first thing you have to do here is this. Remember that B is equal to mu naught I n. So if we determine this one first, you are given the magnetic field, which is equal to the 23 times 10 to the power minus 3, okay, all over the current, which is 18 times 4 pi times 10 to the power minus 10 to the power 7 rather. Okay, so from minus 7. From there, we can get our n, small n here. And after we have determined our n, easily we should be able to determine the number of turns present. Okay, so if you now, after you have gotten the n, we now say, okay, since n, we know the n, we know the small n equal to n all over l. Okay, we can now say the L equal to the number of turn per unit length all over this particular guy. So from there, we can actually substitute what we got here all over this particular guy. So find the all over this guy. So from there, if we do it correctly, so let me just erase so that I can just do it very well. Okay, that is, if we after we have determined that we said B naught equal to, so if we do the substitution, we can actually get, sorry, so if we know that B is equal to mu L-I-N, okay, so which is equal to this guy, which is equal to the mu naught I-N all over L. We can now say this guy is equal to B L all over mu naught I equal to that of n. If after we have determined this one, we can now say, so you cannot say this one is a diameter, which actually make up of a toroid. You can now say, okay, 2 pi Rn equal to 2 pi R B N all over mu naught I. If we do it correctly, we should be able to get 108 meter will be the length of the wire forming the solenoid. That is, we have the magnetic field, and we remember the formula for the solenoid. From there, we make N as a unit of formula. From there, since it's actually in a circular form, that is 2 pi R N equal to this particular guy. So from there, if we do the substitution, we got this one. In case you did not understand the way I did it here, look at it step by step here. I said a solenoid of 1.3 meter long, and this particular guy, we have this guy, the total length of the wire used in making the solenoid is this guy all over this one. From there, do the substitution and you get this one correctly. Okay, let me give you homework to practice at home. The homework is this one. Let me just give you the hint for this homework. We are giving the, how many of you are following? All of us? Yes, not equal. N not equal to this guy. Who says that? But I told you that the N, which is the number of turns per unit length. Okay, so if you look at the homework 2, I said a solenoid of 3 centimeters long has a radius of 0.5 centimeter. It is wrapped with 500 tons of wire carrying a current of 2.0 ampere. The magnetic 2.0 ampere. The magnetic field at the center of the solenoid is what? So here, the simple thing you need to know here is that B, which is magnetic field, is equal to mu naught Ni, which is just very straightforward. Since you know that the mu is what? The mu is 4 pi times 10 to the power minus 7, okay? And we are given the air, we are given the ton, which is equal to number of ton all over L multiplied by that of that of the current, which is 2. So from there, if we do it correctly, you should be able to arrive at this particular answer. Am I communicating? Am I communicating? Yes, your face is covering the question, sir. How is my face covering the question, my friend? Is it for all of us that your face is covering the question? Is it for all or only you, my friend? Why is my face covering the question? I don't know what to do with that one. But okay, I will send the question to you after the class. After I will send the slide to you today. Okay, but okay, let me just give you the last code before I continue. The last code is this: 395 and 8. The last code is 395 and 8. There is no way that can be changed, sir. Why is my face covering the question? Okay, maybe it will be resolved. Okay, the last code is 395 and 8. Let's continue because I still have some 2 or 3 slides for you before I release you. Okay, so how many of you got this question correctly? I said a solenoid is 3.0 centimeter long and has a radius of 0.5 centimeter. But mind you, a solenoid is 3 centimeter long and has a radius of 0.5 centimeter. It is wrapped with 500 tons of wire. Mind you, 500 tons of wire. So the tons of wire, that wire is having this radius of 0.5 centimeter. But mind you, if you fail to use the correct value, you may not get the answer. Okay, so I think I have one question here for you to actually do at home. Before I release you, can you listen to this question? I'm not going to type it, I want to dictate it for you. 2 long ID solenoid. 2 long ID solenoids, bracket open, with radii 10 millimeter and 20 millimeter respectively, bracket close, have the same number of tons of wire per unit length. The smaller solenoid is mounted inside the larger, comma, along a common axis, full stop. It is observed that there is 0 magnetic field within the inner solenoid. The current in the inner solenoid must be, I dictate all over again in case you did not follow. Listen to this question carefully. Listen, I will listen the question all over again. 2 long ideal solenoids, bracket open, with radii 10 10 mm and 20 mm respectively, bracket close, have the same number of turns of wire per unit length, full stop. The smaller solenoid is mounted inside the larger, along a common axis. It is observed that there is zero magnetic field within the inner solenoid. Full stop. The current in the inner solenoid must be option A. Option A, 2/3 the current in the outer solenoid. Option A, 2/3 the current in the outer solenoid. Option B, 1/3 the current in the outer solenoid. Option C, twice the current in the outer solenoid. Option D, half, that is 1/2, half the current in the outer solenoid. Option E, the same as the current in the outer solenoid. So any of you that actually got the question correctly, to actually type it and paste it on your WhatsApp or on Telegram page for others to see. Okay, before I release you, I will continue from here. I will continue from here next week, this week, Wednesday. But mind you, your test is tomorrow. Check the schedule and come as early as possible. We will only allow students to come into the hall during their own time. Don't come when it is not your own slot. Am I communicating? And at the same time, don't come late. Come with your written material, your pencil to actually solve, and make sure you come with your mode of identification. If I cannot identify you, you will not write the test. If you don't have ID card, come with the stamp identification letter from your department. Don't say I did not tell you now. Without mode of identification, you will not write the test. Come with your calculator, come with your pencil or pen, and make sure you don't come with your mobile phone. Don't come with smart watches. If you come, we will not allow you to go in with it, and if it is stolen, it's your own cup of tea. Am I communicating? When you are coming tomorrow, come at your own scheduled time. Don't come when it is not your own. If your own scheduled time is 12 o'clock, you can come 11:30. But if your own is 11 o'clock and you come 8 o'clock, we will not allow you in. Okay? So, and they come with your mode of identification. And at the same time, I wish you all the best tomorrow. Thank you. God bless you. You can bring a plain sheet of paper, okay? You can bring a plain sheet of paper for working. It will not contain what I taught you. It will just be for the first two lecturers, okay? It will not contain magnetic field, okay? Is that okay? It will not contain anything on magnetic field. The first two lecturers that taught you. And make sure you come with your mode of identification. If you don't have student ID card yet, get a signed identification letter from your head of department or from your part advisor. Thank you. If you have not registered, no problem. Just call. I know majority of you came to me and you said you have not registered. If you have registered, it's okay. But if you have not registered, don't worry. Just come. We are going to use the tutorial list for the first semester. Okay. If you have not registered, just come. Don't miss the test. If you miss test, that means it's 0 over whatever. Thank you and God bless you. I will see your face tomorrow. Okay? Thank you.